Let's look at the AC analysis of the push-pull amp. This analysis is done in the same process as we've done for all the other amplifiers. You start off, you draw the AC equivalent circuit. So you transfer the parts over one by one from the schematic to the AC equivalent circuit. Got a couple extra parts now. We've got a couple of diodes in the schematic. In the DC, we consider those to be a 0.7 volt constant voltage. So in the AC, any DC supply becomes a short. So we would just short those out for the AC. Now in reality, there is a little bit of a series impedance with a diode, but it's usually in the low ohms. So if you have these resistors are K ohms and this is 1 ohm, you can pretty much ignore that. The other thing that you might notice on the AC analysis here is that these two transistors, if you look closely at those, they're actually going to be in parallel in the AC analysis. You can see here that the bases get tied together, and the collectors, this collector goes to an AC ground point, so does this one, and the emitters are tied together. Now, you might want to draw that. You might think, well, let's draw that like this. Let's draw it as two transistors. So here's RB1 and RB2, and we show those as resistances to ground. And then I put in Q1, I put in a box for Q1, and I say, okay, in the AC model, the signal is going to get connected straight to the base of Q1, and the collector is going to go to ground, and the emitter is going to go to the other guy's emitter. Then you do the same thing with Q2, and you draw it in. But if you take a look at this, you can see that the emitters are joined together, the bases are joined together, and the collectors are joined together through the ground point. So we don't really need to draw these as two transistors. What we can do is we can draw those as a single transistor. So we might want to draw those as a single transistor and just write down Q1 and Q2. And this kind of makes sense because in the push-pull amplifier, there's two transistors, but each one is only on for half the time. So half the time Q1 is on, and this is how it's connected. And then the other half of the time Q2 is on, and this is how it's connected. So this is how I would draw the AC equivalent circuit for that schematic. And now from the AC equivalent circuit, you can determine the important characteristics of Zin, which I would say is the impedance looking into that circuit. So if I stood here and I looked into this circuit, I'd see this resistor in parallel with this resistor in parallel with this path. So Zin, RB1 parallel to RB2, parallel to beta plus 1 times R prime E plus RL. Z out, I would stand at this point here and I would look back into the circuit and I would say, what is the impedance? I am the load. This is the load here. What is the impedance I'm connected to? And so you would work your way back to the generator here, and then there's the generator impedance. So I'd say it's 1, 2, 3 resistances in parallel, and then I'd come back over here and I'd look at R prime E. So I would say it's RG in parallel with RB1 in parallel with RB2. So those three impedances, 1, 2, 3, all in parallel. But then as I cross the imaginary beta line here, those would be divided by beta. And then I would come back here to this point and I would add in R prime E. So RG parallel to RB1 parallel to RB2 divided by beta plus 1 plus R prime E. Now for the voltage gain, you would write V out over V in, just like you normally do. And then you would write equations of V out and V in with respect to transistor currents and impedances. So V out would be what appears across the load. So V out is this point right here, and that would be the voltage that was created by the current going through this resistor, and that would be IE times RL. And V in, which would be this node up here, this would be all V in here, that would basically be the same current but through the two resistors. So V out over V in would be IE RL over IE R prime E plus RL, which would come out to RL over R prime E plus RL, but R prime E is usually very small. So let's say it's a couple of ohms or half an ohm. So if that was 100 over 100.5, well, that would pretty much be just 1. And that makes sense because when I started talking about the push-pulls, I said that the push-pull, what we did is we took two common collector amplifiers and we merged them together at the common voltage point. Well, the gain of a common collector amplifier is 1. So the gain of the push-pull is 1.